In this video, we're going to look at the general multiplication rule. This is a very important rule, and we're going to use it a lot. So the general multiplication rule is an and problem. And I know we've been looking at, the probability of A and B. But for the general multiplication rule, we would specifically be talking about computing the probability when two events are not independent. And when that's the case, we can use this formula. And basically what's happening is that we're taking the conditional probability rule. So right here, and we are multiplying both sides by the probability of A. So if I take this probability of A and bring it up here to multiply it, I get this formula right here, meaning that the probability of A and B is going to be the probability of A times the probability of B given A. There's an alternate version of this, which is just kind of showing that it doesn't matter what order you multiply these in, but it also doesn't matter what you define as A or B, so I really don't pay attention to this. So let's just look at a couple of straightforward examples of how this plays out. It says 10% of those who apply for a particular job are granted an interview. Among those interviewed, the probability of being offered a job is 0.25. Find the probability that an applicant is offered a job. Well, before you can be offered a job, you have to be granted the interview. So this question is really asking for the probability that the applicant will be interviewed and offered a job. Which means that according to that formula, we're looking at the probability that the person is interviewed times the probability that they're offered the job given that they've been interviewed. This is definitely more complicated than it sounds. 10% of those who apply for the job are interviewed, so the probability of being interviewed is 10% or 0.10. Then it says among those interviewed. So that means that given that the applicant has been interviewed, the probability of being offered the job is 0.25. So that is this probability. And we simply multiply these numbers together and we get, there's pretty straightforward, 0.025. For the next one, it's a similar type of problem. It says, in a certain city, 70% of high school students graduate. Of those who graduate, so that's a given problem, given that they've graduated, 40% attend college. Find the probability that a randomly selected high school student from this city will attend college. So we are looking for the probability that they graduate high school and attend college. So this is the probability that they're going to graduate high school times the probability that they will attend college given that they graduated high school. Again, it sounds more complicated than it is. The probability that they graduate high school, it says 70% of the high school students graduate. So this is 70%. given that they graduated from high school, of those who graduate, 40% attend college. So that's the conditional probability here, giving us 0.28. If the events A and B are independent, then we can simply multiply the probabilities together. And remember, that's because of the definition of independence. If, by definition for independence, if the probability of B is not changed by A occurring, then the probability of B given A is the same as the probability of B. And therefore, this formula that used to say probability of A and B equals probability of A times probability of B given A, well, if they're independent, then this is going to be the probability of A times the probability of B. So let's look at an example. So it says, according to recent figures from the U.S. Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, and 26% in L.A. If one person is selected from each city, what's the probability that all of them are under 18? And then it asks, is this an unusual event? So selecting a student selecting a person under the age of 18 in New York is independent from selecting a person under the age of 18 in Chicago, which is independent of selecting a person under the age of 18 in LA, right? My selection of one person in New York doesn't affect my selection in Chicago or LA, which means that if I want to find these, then the probability that I have a person under the age of 18 from New York and Chicago and LA, because these events are independent, I can just multiply them together. There's no need for the conditional probability anymore. And so I'll take 0.235 times 0.258 times 0.26, which is, where do I have that calculation? There it is, 0.0158. And then when it says, is this an unusual event, remember that an unusual event is an event that's less than 0.05. 0.0158 is less than that, so then yes, this is unusual. So we did this Monopoly game when we were looking at simulations. It says, in the game of Monopoly, if you land in jail, you must roll doubles to be released. If you don't roll doubles within 3 turns, then you must pay a $50 fine. What are the chances that if you land in jail, you will have to pay the fine? So remember, we did this with simulations and we got a variety of different answers. Now let's actually calculate the theoretical probability. So we're going to do this in a couple of different steps here. So the first thing is we're going to figure out the probability that you will roll doubles. This is actually pretty tricky, and I don't have the space or the time really to go through the entire sample space of rolling doubles. But if you think about, you have 2 dice, and the order matters. So if you could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. Or you could get a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6. if you were to write all this out, right, 3 and a 1, 3 and a 2, 3 and a 3, 3 and a 4, 3 and a 5, 3 and a 6, and go all the way through, you'll see that the doubles go along the diagonal. You would have a total of 36 outcomes in the sample space and 6 chances that you get doubles. So rolling doubles is 6 out of 36, which would reduce to 1/6. Then we want to find the probability that you will not roll doubles, because remember, you pay the fine if you don't roll doubles 3 times in a row. So this is a complement. The probability that we don't roll doubles is the complement of rolling doubles, so we would take 1 minus 1/6, which is 5/6. And then it asks, what's the probability that you won't roll doubles 3 times in a row? And can you assume independence? You can assume independence here because the roll of 2 die does not affect any other roll of 2 die. So rolling 2 dice is considered independent events. So then if we want to find the probability that we don't roll doubles 3 times, then that would be the probability that we don't roll doubles, and then the probability that we don't roll doubles, and then the probability that we don't roll doubles again. And when you put this in your calculator, we will get 0.5787. So a little bit higher than 50%, about 58%. So whenever we talk about the general addition rule or the general multiplication rule or the multiplication rule when it comes to independent events, we look at sampling with and without replacement. So with replacement would be that if we sampled one thing, we would pull it out of the population, look at it, and then put it back. That's sampling with replacement. Without replacement means that we sample it, we pull it out. I'm thinking of pulling something out of a hat or a drawer or something like that. We pull it out and we don't put it back before we pull out another sample. So that's without replacement. The sampling with replacement, when we put it back, means that we never change the sample space. We never change the population, which means that the denominator is not changing and we have independent events because the pulling of one sample, because I'm putting it back, doesn't affect the next pulling of a sample. Whereas if we're sampling without replacement, then when I pull out a sample and then I keep it, I've now changed the sample space, which means that I don't have independent events. My next pull of a sample, that probability has changed. So we're going to look at 2 examples, one with replacement and one without replacement. So let's say we have a box of marbles. We have 7 red marbles, 3 green marbles, and 6 black marbles. So this would be 16 total marbles. And let's say we draw one marble, put it back, and then draw another, which means that we are sampling with replacement. We're putting it back. Are drawing marbles with replacement independent events? Yes. One draw does not affect the probability of another draw. So let's find the probability of drawing 2 black marbles in a row. So we're looking for the probability that we're going to draw a black marble and another black marble. But we're replacing it, so this is going to be the probability that we draw a black marble times the probability that we draw a black marble. It's not going to change. We have 6 out of the 16 black marbles, so the probability that we draw a black marble is 6 out of 16. We put this first one back, so the second one has the same probability, 6 out of 16. Put this in your calculator and you'll get 0.14. Again, don't reduce the fractions. Just use the fractions to show your work. Write the decimal as your final answer. What's the probability of drawing 1 green marble and then 1 red marble? So we're drawing a green and then a red. Because these are independent, this is the probability of drawing a green times the probability of drawing a red. We have 3 green marbles, so 3 out of 16, and 7 red marbles, so 7 out of 16. And this will give us 0.082. The last one, find the probability of drawing 1 red marble and then 1 marble that is not red. So a little bit of a complement here. So we've got the probability of a red marble and then a not red marble. Again, we have 7 red marbles. So this is the probability of drawing a red marble times the probability of not drawing a red marble. So the probability of drawing a red marble, we have 7 red marbles. If there are 7 red marbles, then there are 9 marbles that are not red, right? 1 minus 7/16, or 16 minus 7. And we multiply these together. But usually, if we are drawing marbles or something like this, we don't put them back. So let's look at the same scenario, but this time without replacement. So we are now going to draw a marble out of this box and not put it back before drawing the next marble. And I don't have the summary here, so we have got 7 red marbles, 3 green, and 6 black. And this gave us a total of 16. So are drawing marbles without replacement independent events? The answer to this is no, because one draw does affect another draw. So now if we want to find the probability of drawing 2 black marbles in a row, so we want to find the probability of drawing a black marble and then another black marble. I'm not going to write out the full formula because I really want you to kind of just think about the totals here. So we have 6 out of 16 that are black marbles. So this first probability is 6 out of 16 that we're going to draw the first marble to be black. But now we're going to pull that marble out and not put it back in the box, which means now we only have 5 black marbles left and only 15 total marbles. So the probability that we now draw another black marble, we've reduced the number of black marbles and we've reduced the total number of marbles. So this has changed our second fraction. And when you put this in your calculator, you get 0.125. If I want to find the probability of drawing a green and then a red, we have 3 green marbles out of 16. So the probability that that first marble is green is going to be 3 out of 16. But now I'm not replacing it, which means the total number of marbles has been reduced to 15. But I haven't changed the total number of red marbles. I drew out a green one. So there are still 7 red marbles in there. When you put this in your calculator, you get 0.0875. And then finally, if the probability of drawing 1 red marble and then 1 marble that's not red. So we have the probability of drawing a red and not red. We have 7 red marbles, so the probability that the first marble is red is 7 out of 16. We're not putting it back, so it's reduced our total number of marbles to 15. But the marble we pulled out was red, so it hasn't reduced the number of not red marbles. And not red was green and black, so 9 marbles are not red. So if we do this multiplication, we get 0.2625. Those are some examples without replacement. Another place that we see the general multiplication rule is in tree diagrams. And these can be pretty challenging. So I have an example here, and then I have another example in the example videos. So this says a utility company in a large metropolitan area finds that 95% of its customers pay a given monthly bill in full. Looking more closely at their records, they find that 98% of the customers who pay one monthly bill in full also pay the next monthly bill in full. So notice that you're given a conditional probability. Only 10% of those who pay less than the full amount one month will pay in full the next month. I always feel like you know when it's a tree diagram when it feels like a crazy riddle. But we have 2 scenarios here. We have the person is paying the bill in full or they're not. And then we have a conditional probability on whether or not they're paying the second bill or not. So the first bill, we have 2 scenarios. They either pay in full in any given month, or they don't pay in full. Right, and we're told that the probability that in any given month that they pay in full is 0.95, which means that the complement is that they don't pay in full. And remember, complements add up to 1, so the probability that they don't pay in full is 0.05. Now we have 2 separate scenarios for each of these scenarios. So if they pay 1 month in full, then they can either pay the next month in full or not pay the next month in full. And we have those same 2 scenarios for if they don't pay the first month in full. So they could not pay the first month in full, but pay the next month in full. Or they don't pay either month in full. So we want to find the conditional probabilities to these 4 scenarios. So it says that 98% of customers who pay one monthly bill in full will also pay the next monthly bill in full. So 98% of the 95% will pay both months. I hope that's making sense. So we have 95% of the customers, 98% of these will pay the next month in full. So again, we're using complements. Oh, let's figure out this. This is 0.931. Using complements, that means that 2%, if 98% pay the next month in full, then 2% don't pay the next month in full. So 2% of this 95% will not pay the next month in full. And this is 0.019. Then it says only 10% of those who pay less than the full amount one month will pay the full amount the next month. So that's this scenario. They pay less than the full amount the first month, but then they pay the full amount the next month. So 10% of these 5% are in that scenario. So this is 0.005. Which means that 90% of these 5% don't pay either month in full. And this will add to be 0.045. So I have a lot of complements in here, and I have a lot of rows that add to 1. So just looking quickly here, this 0.95 and this 0.05, those are complements and they add to 1. Then I have these complements that add to 1, and these complements that add to 1. And then I always check my work, because the 4 totals that I'm left with at the bottom, if I add all 4 of them up, they should equal 1. Right? These 2 should equal 0.95 when added up, and these 2 should equal 0.05 when added up. So this is the tree diagram. It's challenging, but once you do a few of them, it's not too bad. Let's use this diagram to answer some questions. So I brought that diagram over here in a picture, and let's actually answer some questions. So the first one says, find the probability that a customer chosen at random will pay 2 consecutive months in full. So we have that in our diagram. They pay the first month in full, and given that they pay the first month in full, they also pay the second month in full. And this was 0.931. So we're following that branch of the tree. The next one says, find the probability that a customer selected at random will pay neither consecutive months in full. So now I'm looking at this branch of the tree, where we have a not pay in full and a not pay in full. So they don't pay in full the first month, and then given that they didn't pay in full the first month, they also don't pay in full the next month, giving us 0.045. Then it says, what is the probability that a customer chosen at random will pay exactly 1 month in full? Notice it doesn't say which month, so I actually have 2 branches that fulfill this requirement. They could pay the first month and not the second month, so this one. Or they could not pay the first month but pay the second month, this one. So I'm basically, and did you hear me say or? It's either this one or this one. They're disjoint events, so I can just add up those probabilities. So I'm going to kind of show all of my work here. I'm taking the 0.95 that they paid the first month and not the second month, or they didn't pay the first month, but they paid the second month. Which means I'm taking this 0.019 and adding the 0.005. And that is 0.024. This last question is considered a reverse the conditioning question. So it says, if a person paid the second month in full, what's the probability that they paid the first month in full? So notice they kind of switched the direction on the tree, right? Our tree shows the conditional probabilities of if they paid the first month in full, what happened in the second month. Now they want us to go in the opposite direction. This is where you should use this is a given problem, so you want to use that formula. So what this is asking is, what's the probability that they pay the first month in full? Let's see, I'm going to say pay month 1 in full, given that they pay month 2 in full. That's what this is asking. So given that they paid the second month in full, given that, what's the probability that they paid the first month in full? So using our formula, this is the probability that they pay both months in full. So they pay month 1 and month 2 in full, divided by the probability that they pay month 2 in full. So I hope I don't run out of room here. I'm going to move over. So the probability that they pay month 1 and month 2, we actually found this in the first part of the question. So we're looking here, month 1 and month 2. So the numerator is going to be 0.95 times 0.98. The denominator is that they're paying month 2 in full, and there's 2 of those scenarios, this branch and this branch. So it's going to be 0.95 times 0.98 plus the other time that they paid month 2 in full, which is 0.05 times 0.10. I know this looks complicated. Don't cancel anything. Just find these numbers. So this is 0.931. We found that in part A. In part B, or in the denominator here, if we multiply and add these together, we will get 0.936. And then when you divide, you get 0.995. I think this is my last slide. Let me look. Yep. All right, one more video after this.